So if you want to find the work required to stretch or compress a spring, to grab it, pull on it, how much work is done by you to stretch that spring or to compress it? Well, the equation for that, the work done by a spring, it's equal to 1/2 kx squared. Again, k is the spring constant. So let's see if we can find an example. We have a toy. A toy that has a spring constant K equal to 230 Newton per meter. How much work is required to stretch the spring spring 2.5 centimeters. After the class yesterday, because I was talking about cars and spring, and I really didn't know much about cars. I made that from minute one. I don't know much about cars. I know I need a car to get me to work and take me back home. You change the oil every 3,000 feet, 3,000 miles, I mean, not 3,000 feet. Yep. 3,000 miles and put gas in it when it's empty. That's all I know about cars. But we're talking about the tab yesterday. I'm going to shrink it down, drop it by about a half a meter. So I start looking at what is K for a spring in a car. So a car actually, K, here we go. K is equal to roughly 21,000 Newton per meter for a car, for an average car. That's a sneeze?
Yeah.
I shake the whole building when I sneeze.
Same.
So now, if we apply, how many joules do you want to put there? Pick some numbers for joules. How many joules do you want to put on that car? 200 joules of work is done to compress this spring. I'm talking about the car here. So what is X? The compression. How much did it compress? What is X? So two different questions, completely different from each other. One deals with the toy, the other one deals with the car. So the first one says, how much work is required to stretch the spring 2.5 centimeters? Well, so question one is straightforward. Work equals what? 1/2 kx squared. The work is unknown, we're looking for it. 1/2, we know what k for that toy there, which is what? 230. We know the distance is going to compress it 2.5 centimeter, that's what? 0.025 meters. And you're going to square that. Make sure you convert that to meters. How much work is done? 0.07 0.072 roughly joules. Not a lot. Now let's look at your car. You're applying 200 joules of work. Again, work equals 1/2 kx squared. The amount of work here is what? 200 joules. 1/2 times 21,000 times x squared. 200 equals what? 10,500 x squared. We won't even notice it in the car with 200 joules. 200 divided by 10,500. 0.019. What is x equal to? Take the square root of that number. 0.14 centimeter. Is it 0.14? Actually, that's meter here. 14 centimeters. Actually, that's not small. For some reason, I thought it would be much smaller than that. It will compress 14 centimeters. If the value of the force is changing, that's what happened to the spring. When you stretch the spring, that value is not the same. When the spring is close to its natural position, the force is not that large. But when you stretch it really hard, the value of the force is much larger. So when you look at the force, if you were to graph that and see what the force looks like on a spring, it will look something like this. Like if this is the compression or stretching, and this is the force, that's x here, and this is the force F. You will find when the force is its natural length, there is nothing. When the spring has natural length, there is no force. You're not pulling, you're not pushing. But as you start to pull, you'll see the force goes like this. The more actually that you stretch it or compress it, the larger that force is. So all the other examples we dealt with, every single example, our force was constant. Remember that dad pushing, or you were pushing the baby in the stroller? I forgot what I called the story. That force was the same. It was constant, 400, right? That means if you were to graph that, that force was like this, horizontal. It never changed. But now when you're dealing with the spring, that force is actually changing all the time. That's called variable forces. So your force is a variable force. It changes. And if we want to do it from here to there, let's say I want to calculate what the force to go from here to there. I'll put some numbers. There's 0, 0 here, and this is, we'll say 10. And let's say this is 20, the force. So if I want to find out the work done to stretch that spring from 0 centimeter to 10 centimeter, what am I going to do here? I don't know what K is. I know the work done is 1/2 kx squared. And that's what? 1/2 K times X times X. That's what X squared is. And what's K times X? Isn't that the force of a spring? We use negative just to indicate the direction times X. So when you look at that picture here, so what am I going to use for a force? Is 0 down here, is 20 right there. Well, what should I use? Do I use a 20 from 0 to 10? Do I use the 0? Do I use a 5? What would I use? The only fair value to use now is what? The average number. What's F average? In this case, the average value is what? 20 plus 0 divided by 2, that's a 10. To find the average of two numbers, you add them and divide by 2. So if you want to calculate what's the work done by the spring here, you have to use the average value. So that's going to be 1/2. My average value for this example is 10, and my distance is 10, and that'll be 50 joules. But I can't use the 0, I can't use the 20, I can't use the 18, the 4. I have to use the average value.
Didn't you say that you add the 2 and then you divide?
Correct. Add them and divide by 2. What's 0 plus 20?
Oh, 0. Okay.
Yep. To find the average of any two numbers, you add them and divide by 2 always.
No, it's just I thought you were using
Yep.
the 10.
So let's take an example with springs. Different example. Yesterday we talked about a runaway train. Was it yesterday? We talked about spring or the day before? So this is the same idea. I'm going to have this story here. I have a spring who's sitting right there, attached to this wall there. It's not moving. And there's a block of wood moving toward the spring. So we have a block of wood. The mass is, I don't know, 1.5 kilogram. It's moving that way with the speed, initial speed of 2.2 meters per second. I'll pretend there's no friction here. This is on a table. Nice smooth table, there's no friction. If there's no friction, that speed will continue 2.2 till it hits that spring. What happens when it hits the spring? It's going to compresses the spring, and the block of wood is going to stop here. Then if there's no friction, it's going to come slow till it stops, then it goes backward in the same direction it came in, it goes flying. I'm going to look at that instant, right there. The block comes in contact with the spring right here. Compress it how far? For a little bit. I don't know how much we compressed this. We went from here to here. That distance is unknown. That's how much we compressed it. But when the block reached this point, that's the 1.5 kilogram, what was the final velocity here? 0. Stopped. Can we find x? The only thing I'll give you a spring constant, k, Let's say K equals 475 Newton per meter. Now let's look at this right here. How much kinetic energy right here did the block have? Initial kinetic energy. The only kinetic energy we had is what's in this one, which is 1/2 the mass times the velocity squared. The mass is 1.5. The velocity is what? 2.2 squared. I got 3.6 joules. How much energy in that spring? Right there. What did I use for a symbol for energy for a spring? I just didn't write anything. How much energy initially in the spring? Was that spring compressed or stretched initially? Nope, nothing. Wasn't touching. It was just laying on the table, sitting by itself. So it wasn't stretched or compressed. 1/2 kx squared. K is 475. X is 0. That's really 0. What's the total energy initially? It's going to be 3.6 joules. You add these two numbers. Now let's look at the final, when the spring actually, when the block came in, pushed it till it stopped moving and stopped right there. What is the kinetic energy of the block here? 1/2 the mass, which is 1.5. And what's the velocity of the block here? 0. What about the spring? That's the final action, not initial. We have 1/2 kx squared. 1/2 k is what? 475 times x squared. What's 475 divided by 2? 237.5. So there's one answer. There's the other answer. What's the total number here? (237.5 x squared). And what do we know about these two numbers? If there's no friction, these numbers should be what? Equal to each other. It's called conservation of energy. If you have no friction, you're always going to have conservation of energy. So the initial, we'll call that initial here, should equal the total final energy. And what's the initial? 3.6 joules. And what's the final? 237.5 x squared. Can I get x squared out of that? I got 0.015. What's x equal to? 0.12 meters. 12.3 centimeters.